Welcome back to Physics 142. In this video, I want to try to bring a few of the things that we've learned so far this semester together all in sort of one place. All right, and in doing this, we're going to write down what is often referred to as Maxwell's equations. All right, after a scientist in the 1800s who sort of wrote this down and brought these concepts together. So let's do this. All right. So in electricity and magnetism, what are the things that we've talked about so far, sort of in summary? All right. Well, what we started with is we started with the idea that charges create electric fields, right? And we had several ways of writing this, all right? But one of the ways that we wrote this down is through Gauss's law, all right? Gauss's law said that the flux going through some surface, if you had a closed surface, right? Basically, if you put more charges in that closed surface, you got more electric flux. You got more electric field coming through that surface, right? So this was Gauss's law. Gauss's law essentially was telling us that charges produce electric field. Right? The more charges you put in, the more electric field you get out. All right? Great, that was Gauss's law. The next thing that we learned is that, so that was sort of the big deal in electricity. Then we moved to magnetism, all right? And in magnetism, we realized it's not charges, but it's moving charges that create magnetic fields, all right? So just as charges create electric fields, moving charges or currents create magnetic fields, right? And so we wrote that down here with Faraday's law, right? That we said if you draw some loop around some current, all right, the more current you have enclosed in that loop, the more magnetic field you get. Okay, so these two laws sort of went together a little bit, right? This told us that charges produce electric field. This told us that moving charges produce magnetic fields. All right. Now, another interesting thing about magnetism, all right, these laws look a little bit different, and one of the reasons they look a little bit different is that there aren't any magnetic monopoles, right? So if you just had magnetic charges, right, like just a single plus magnet, that would be really cool, all right? But we don't. Magnets always come in pairs, and so we realized that if you have a closed surface, right? If you close some surface and you try to put magnets in it, all the field lines any field line that comes in will also go out again. So you don't end up having any magnetic monopoles, all right? So, if I was to write this rule in words, this would be magnetic monopoles don't exist, all right? That's what that says it, right? That you don't just have a charge that makes a B field, all right? This here, Gauss's law, is telling us that charges make E fields, right? Charges are a way of making E fields, so that's good, right? This is an electric monopole, right? Electric monopoles create E fields. And this right here, right, this is saying current or moving charges create B fields. So, all right, that's great. All right, moving charges are making B fields. Charges, just isolated charges, they make E fields. But things have gotten a little bit more complicated recently because we realized that, well, if you changed the magnetic field, specifically if you changed magnetic flux, right? So this isn't a closed surface anymore, right? But just, the flux through some window, some window, if you're thinking about the magnetic flux through that window, right? If we change that flux, then that actually ends up being another way of creating an E field, right? We realize that creates a potential difference, right? This creates a V or an EMF, right? And where does that EMF come from? Well, it comes from these non-conservative electric fields, right? These electric fields that sort of loop in circuits. So what we realized is that you can induce an E field by changing B fields. Wow, that's not very easy to read there. I apologize about that, all right? But this is pretty cool. We actually have a second way of making an E field now, that you can make an E field by changing the B field, all right? And so and I think I said this wrong earlier. I might have called this Faraday's law. This is Ampere's law, right? This was Faraday's law. So Ampere's law, Faraday's law, Gauss's law, and this one isn't named after any scientist, so you just maybe call it the magnetic monopoles law or something like that, right? But this is kind of cool. So in addition, we have another way of making an E field. If you change the B field, you get an E field. So this, we're sort of seeing a little bit of symmetry here. And when Maxwell wrote all this down, it sort of brought up a question, right? And the question was, well, all right, we actually have two different ways of making an E field. We can make it with charges, and we can make it by changing the B field. But right now, we only have one way of making a B field. We make it by moving charges. Is it possible that that there's another way? That maybe you could, if you changed the E field, could you induce a B field? Well, the answer to that ends up being yes, all right? It ends up being true, all right, that, and this is, it ends up being true that if you change electric flux, all right, then you induce a B field. So it turns out that this kind of works in reverse, right? If you change the electric flux, you can, in fact, induce a B field. This gets a special name. It's called a displacement current. A displacement current. And I'm just going to make sort of a units argument as to how this works, all right? So if we think about electric flux, all right, electric flux is something here like in Gauss's law. So unit-wise, we know that that's Q over epsilon naught, right? That unit-wise, electric flux is Q over epsilon naught. So if we change the electric flux, right, we do d phi dt, then that's going to be dq dt times 1 over epsilon naught, right? So that'd be the derivative of both sides. And so if I multiply the epsilon naught over to the other side, so I'll just go ahead and do that, all right? Multiply the epsilon naught over to the other side. dq dt, well, that's a lot like current, right? That's a lot like some sort of current, right? So changing electric flux essentially is making some sort of current. And Maxwell realized this, and he realized, well, hey, there's a place I know where current fits into this, right? Current fits in right here, okay? So what Maxwell did is he said, well, what if I just add a current term to this? Right? What if I add epsilon naught times d phi e dt, all right, times that changing electric flux. And well, to make the units work out, I need this mu naught. I have to distribute the mu naught, right? So I'm going to go ahead and distribute that mu naught, okay? So, I'd put all the current in parentheses, right? If this is like current, right, this is a lot like I. So the mu naught gets distributed. So you end up adding an extra term here to this equation. All right, and when you do that, what this says now is this term here is saying that you can induce a B field by changing E fields. And that is pretty cool. And so these equations here together, these are called Maxwell's equations. And in a sense, they summarize everything that we've learned here in electromagnetism. What we've learned is that there are two different ways of making electric fields. You can do it with charges, or you can do it by changing your magnetic field. All right? And there also are two different ways of making magnetic fields. You can do it with moving charges, or you can do it by changing your E fields. And so there really is a lot of beautiful symmetry here in Maxwell's equations that are really telling us some deep and fundamental things about how charges, electric fields, and magnetic fields work together. We can actually take this and use this to understand how we produce light from charges, and I'll do that in the next video.